Welcome to Mr. Frolic's physics classes. In this lecture, we will see the first part of the study of simple harmonic motion. Hello there. In today's lecture, we're going to start talking about simple harmonic motion. And before we dig into simple harmonic motion itself, we need to make sure that a couple basic definitions are in and we all have the same understanding. So the first thing I want to talk about now here is the concept of periodic motion. So a periodic event is something that repeats itself at regular time intervals. Example, the publication of a weekly news magazine like the Times magazine. Every week you have a new issue. Perhaps the publication of a newspaper like the New York Times. Every day you have a new issue. When we talk about periodic motion, is motion that repeats itself from time to time. So please copy this down. Periodic motion is when the object will pass by the same position with the same velocity and the same acceleration at regular time intervals. Okay? Now, have we already studied any example of periodic motion before?
I think so. Is the uniform circular motion a periodic motion?
Exactly, Mary Jane. When we studied uniform circular motion, this was our first example of periodic motion. So if I just pick a point here of the path, my particle will be passing by this very same point with the very same velocity and under the very same acceleration at regular times. And that was our very first example of periodic motion. About periodic motion, there are a couple things that we need to define. The first one is the idea of period, which we represent by capital T. And period is going to be, by definition, the time it takes to complete one cycle. So period is the time it takes for this object here to go around the loop and complete one cycle. Is measured in units of time. So period can be given in perhaps hours, minutes, days, but the international unit for time is second. So in our study, period is actually going to be measured in seconds. I have in here a simple pendulum, okay, which is a point mass hanging from a massless string from a fixed point. And I want to see roughly how we could count periods of oscillation of a pendulum, for example. So I have here a green line marking for me roughly the vertical direction. I'm going to pull this a little bit to the side and then count period. Let's see how it goes. 1, 2, 3, 4, 5, 6, 7. Is this what I'm doing right?
I don't think so, Mr. Frolic.
Why, DJ?
I guess you are counting too fast. The pendulum passes by the same point, but it is not moving in the same direction.
Interesting. Tell me now if this is right. 1, 2, 3, 4, 5.
I think that now it is right, Mr. Frolic.
Yes, now it's right. Now I'm counting the particles passing by the same point, with the same acceleration, but also with the same velocity. Otherwise, it's not fully repeating itself. The other concept that we need to understand, other thing that we need to relate in here, is the idea of frequency. Represented by a letter F. And frequency is how many times a periodic event happens on a given time interval. Okay, so that's the best definition for frequency, I think. In terms of mathematical expression, frequency will be defined as number of times the periodic phenomena happens on a given time. If we consider just one cycle, n equals 1, the time interval that I'm considering is going to be the time to do one loop, which is one period. And then my equation for frequency becomes 1 over period. So frequency is the reciprocal of period and vice versa. In terms of units, frequency will be given in anything of 1 over time. But the international unit for frequency is hertz. And we usually represent this by Hz. Okay? So, have you all, any of you guys, ever heard or remember this unit of hertz? Yes, Mark?
My favorite radio station is the 100 megahertz on my dial.
Yes, you're right. When you say that the radio station is 100 megahertz, you just tell me that the wave signal that they sent to you oscillates 100 million times per second. That's exactly what this here represents for us. Okay? So, in terms of concept, period could be related to how long it takes for something to happen, and frequency could be related to how often something happens. The next kind of system we're going to study that we will see will be periodic is the mass spring system. So let's consider here a spring whose normal length, L, would end exactly at this point here, my 0 and my coordinate. And I will compress the spring, okay, push a block of mass M against the spring and compress it until I am at a position here, which I'm, instead of calling X, I'm just going to call negative A. This block has a mass M, and the spring is compressed at position negative A. It has zero velocity at that point, but we have a very strong spring force pushing it out. Well, once I release the system, the spring force is going to accelerate this block, and it's going to make it move towards my 0 point. Once I reach the 0 point, my block will be right here, it will be moving with a maximum speed this way. And the spring force on it is going to be 0, because that's the position of neither compression or stretch. Then the block will keep on going. But once it starts to keep on going, it will start stretching the spring. So this spring will now stretch, and when it starts stretching, it will slow the block down. And this block will stop at a position here, x equals a. And once we get to that point, the velocity of the block will be 0. So this is the turning point. And I'm going to have a spring force that is going to be pulling back on the block. This spring force now is going to make the block come back in. And I'm going to have my block accelerating until, again, x equals 0. This way, and is now going to have a speed Vmax, but just in the opposite direction. And the force on the block at that point is going to be 0, because it's no longer pushing. Well, this block is going to move on and compress my spring. Until it stops right here at a position x equals -a. And again, at this point, I'm going to have a maximum spring force pushing it out. Okay? So one period is, for example, when it goes from this point all the way down to this point. It's a complete back and forth. I'm going to go from maximum potential energy to maximum kinetic energy, maximum potential energy on the opposite end, then it's coming back, maximum kinetic energy in the opposite direction, and then maximum potential energy. So this is basically the description of my mass spring system oscillating in the horizontal direction. To represent my system in my spring system, if I hang the spring in the vertical direction, I'm just going to consider in here a spring with a position marker and a little hook. So my normal initial situation of the spring would be roughly something like this here. This is my spring very compressed. And when I hang a certain mass to it, my spring will stretch all the way down to here. Oops, right here. Well, and here then is my mass. My system is at rest at this point under the influence of Fg and spring force. Now, if the only thing I'm going to study is the oscillation of a mass spring system on the vertical direction, one thing we can do to simplify things is just shift the 0 point to here. So I'm going to start analyzing from this point in a way that if I pull this object down an extra distance, like down here, we will consider the amplitude to be this. And you can see that this object will roughly oscillate up and down between these two positions here. Okay, so it's going up and down and oscillating roughly between the two positions. Now, because of frictional losses, of course, this amplitude is decreasing over time. Let's count in here now periods of oscillation. Measuring here, going down 1, 2, 3, 4, 5, 6, okay? So that's how period should be counted. In this video, a mass spring system is compared to a rotating disc. The red dot helps us keeping track of the rotation of the disc. When the mass is pulled down from its resting position and released, the mass oscillates in the vertical direction. The position of the mass coincides with the vertical position of the red dot. The motion of the mass is identical to the vertical motion of the red dot.
That's so cool.
Our next step now is to see how period and frequency will be related to my uniform circular motion, which was our very first example of periodic motion. So if you remember, when my particle is moving around the circle, going from position initial to, for example, a final position F, the vector position R, this vector that goes with it, will swipe an area A and would actually move an angle theta. Okay, if you cannot read well, the only thing that I wrote in here is theta. And if you remember, the angular velocity, omega, is by definition d theta dt. Okay, which now when I consider one loop, omega is going to be, in one loop, the angle that we'll describe is one full circumference, which is 2 pi radians. And the time to complete one loop is actually 1 period. So omega equals 2 pi over t. If we now remember that frequency is the reciprocal of period, I can also say that omega equals 2 pi f. And then that will be how period and frequency are related to uniform circular motion. After we saw the relationship between a harmonic oscillator and either the y component of a uniform circular motion, which is what we saw on the short clip, or perhaps the x component of the circular motion, what I'm going to do is use the uniform circular motion, study its x component, to gain more insight on the properties of harmonic motion. I'm going to use the x component just so my equations would look like the standard equations. So we're going to start with this here. Let's assume that I have in here a particle that's going to be moving in uniform circular motion on a circumference of radius a. Okay, so we're going to assume that the radius of the circumference is a. And this particle is, at a certain moment, at a position located here by the angle theta. The x component of this particle is going to be here. This is its x component. And this x component is going to be actually a cosine of theta, because it's adjacent to theta, a cosine of theta. Now, the angle theta itself is not a constant. It's changing, and then it becomes a function of time. Theta can be written as a omega t plus theta naught, where theta naught would be my initial position. Now, in this topic, we usually don't write theta naught. We write phi, and phi is usually known as the phase of the angle. This name is going to make more sense when you study waves, which is not going to be done in our course over here. So, if now I combine this with my idea of x, x of t is going to be then a cosine of omega t plus phi. So this is just my equation for position of my harmonic oscillator. Now, the velocity is right here, tangent to the path, and in the direction of motion, I'm assuming that this is moving counterclockwise in the trigonometric cycle. The x component of the velocity is going to be here, right here, Vx. And the angle theta now is up in this point. So Vx is going to be a V sine of theta, but because it's in the negative direction, I can also do this as negative V sine of theta. So my equation for velocity, V of t, then becomes negative V sine omega t plus phi. But V in uniform circular motion equals the radius multiplied by omega. So my equation for velocity then becomes negative omega a sine omega t plus phi. Because we are a calc-based class, I also want to show you how I could reach this result by using calculus, which of course is faster and nicer. So I can just say that V is dx dt, which is going to be then the derivative of x, which is a cosine omega t plus phi. A cosine omega t plus phi. Well, that derivative is going to be then the derivative of the cosine, which is negative sine of omega t plus phi, multiplied by this constant a, and also after this I need to use the chain rule and take the derivative of the argument omega t plus phi. But the derivative of omega t plus phi is just omega. So V of t through calc-based derivation becomes negative omega a sine of omega t plus phi. The acceleration of this motion is completely centripetal. So I have my centripetal acceleration here. And the x-coordinate of that acceleration is going to be right here, ax. The angle theta is exactly this one. And if I reason the concept, this ax is going to be negative A cosine of theta. So my x component, A, as a function of time, is negative A cosine omega t plus phi. Now let's remember that in uniform circular motion, the centripetal acceleration is r, which is the amplitude, omega squared. So my acceleration here becomes then negative omega squared A cosine omega t plus phi. If I use calc, I know that acceleration is the derivative of velocity. So my acceleration is going to be then the derivative of negative omega A sine omega t plus phi. Now, parenthesis here. Well, negative omega A. The derivative of sine is cosine of omega t plus phi. And I need to apply again the chain rule to take the derivative of the argument, omega t plus phi, which we've seen before, just produces another omega. Omega squared A cosine omega t plus phi. So on the left, we have the equations derived just by analyzing the vectors. And on the right, the same equations derived by using derivatives. If now we look at the equations of motion that we derived for my simple harmonic motion using the x-coordinate of the uniform circular motion. When we look at x of t, a cosine omega t plus phi, and the acceleration, negative omega squared, a cosine omega t plus phi, we can identify that this here, a cosine omega t plus phi, is actually the position of the object. And from here, I can say that the acceleration is equal to negative omega squared times the position. Okay? So the acceleration of the object is equals to negative omega squared times the position. Notice that omega can be positive or negative, but omega squared is always going to be positive. So this equation here tells me that, one, the acceleration is always in the opposite direction of position. They're always anti-parallel. Number two, that the magnitude of the acceleration is always proportional to the magnitude of the position. And this is very important for us. This is how we identify simple harmonic motion. Any motion, any, does not matter how crazy it is, whatever it is, if I can identify that the acceleration of this motion is equal to negative omega squared x, this is going to be now considered simple harmonic motion. These equations were derived for uniform circular motion. I claim that the mass spring system will actually work the same way. Let's see how we can apply this idea with the principles of what we had before, and then get this straight to the mass spring system. So I'm going to start with this here. A mass spring system, the driving force is the spring force. And this spring force equals negative kx. Now, this spring force is also the net force, mass times acceleration. So if I combine the two, ma equals negative kx. Or A equals negative K over M X. Well, notice that K over M is actually a positive constant. And we will identify K over M as being omega squared. So, omega squared for a mass spring system is K over M. Now let's hold on this here. Let us remember that in uniform circular motion, omega is 2 pi over period. Therefore, period is 2 pi over omega. But if omega squared is K over M, then period is going to be 2 pi square root of 1 over K over M, which becomes M over K. And this here now is the period of the mass spring system on an oscillator. This equation is given to us on the AP equation booklet. You don't need to memorize, but you need to understand the process. Frequency is the reciprocal of period. So frequency then is going to be 1 over 2 pi square root of K over M. And this is the frequency of this mass spring system. And this equation is also given to us on the IB booklet. Notice again that this first part here, this reasoning here, and this one are from the generic uniform circular motion idea. In here, I'm writing down now my equation specific to the mass spring system. And I'm just telling you that the mass spring system is an equivalent system to the uniform circular motion X component or Y component. This concludes the first part of the Simple Harmonic Motion lecture. You should now practice some exercise and ask me the questions you may still have.